Hi, my name is Ash Whitfield, and this is my video report for Lab Experiment 2. First, we'll start with our lab introduction and background info. Lab overview and purpose. Our experimental setup is as follows. I dropped a loosely balled up piece of paper from a specified height, I recorded its motion with a camera, and analyzed it in tracker software. Purpose of our lab: to compare the position versus time data of observed freefall motion and computationally modeled freefall motion, drag and no drag, to better understand the mechanics of motion. Results preview. The motion predicted by the model with no drag resulted in positions with greater magnitude as opposed to the model and observations that account for drag. Physics principles and assumptions. Newton's second law. F net equals ma, or an object's acceleration is determined by the net force that is acting upon it and the object's mass. Our forces are as follows: force due to drag, formula seen here, and force due to gravity, formula seen below. The J hat components are important, as F grab acts downward as seen in the model, and F drag acts upwards, opposing motion. Related equations are the velocity update formula and the position update formula, seen here. System and initial conditions. Our system is our paper ball, and our surroundings are air, floor, hand, and everything else. Initial conditions are 0.0177 meters in the positive y direction, which was used for all models and observations to maintain consistency. Our initial velocity is 0 meters per second. The mass of the paper ball is inconsequential for our analysis, as it is treated as a constant. You can see the EdStem thread for reference. J hat is right here. Computational model details. Our initial ball position is our initial position mentioned on the previous slide. Our ball velocity is 0, and our t is 0 initially. Our constants and our values are as follows. Our j hat, as specified earlier. Our b is 0.3355, found by guess and check. Our delta t is 0.03333 seconds, and our g is 9.8. Our F grab is the mass of a ball times g times negative j hat. Our force due to drag is negative b times the ball's velocity squared times j hat. And please note that when b equals 0, F net equals F graph, gravity-only computational model. So all our code can be used in the gravity-only computational model when b equals 0. Our F net is equal to F graph plus F drag. Update formula applications are seen here and here. Results. Here's a table of our results, but I feel it's better to represent them in a line graph to show the difference in the later t values. Results explanation. We can see that all three lines are practically identical at low values of t. Both of the datasets that account for drag follow the same path through the end of the recorded time period. These are the blue and green lines. The data that ignores drag trends lower than the other two in the later portion of the time period. This is because we know that the effect of drag increases proportional to the square of the velocity due to the formula, so as gravity accelerates the ball downwards and velocity increases, so does our drag force, resulting in smaller displacements over a given interval. This graph exemplifies the opposition to motion that drag force provides, as the model neglecting drag resulted in greater displacements overall. Possible sources of error. Imperfect tracking in our tracker application, as humans are fallible. Slightly imperfect b value, as the b value is found via guess and check as recommended on EdStem. Conclusions. What does it mean? Which models, if any, predict a terminal velocity? And what does it mean for the net force? When the force of gravity acting downwards cancels out the force of drag acting upwards, terminal velocity is achieved. Because the forces cancel each other out, we know that F net on the object equals 0. And because drag is a necessary component to achieve terminal velocity, the model that accounts for drag predicts a terminal velocity. In a model without drag, the constant force of gravity causes the object to accelerate downwards infinitely with no maximum or terminal velocity. What if? Imagine that the object was initially thrown downwards. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The terminal velocity would be the same regardless if the object was initially dropped from rest or thrown downwards. This is because F net equals 0 equals the force of gravity plus the force of drag, because the directions are accounted for. in these steps right here. And since the force of gravity is constant and the forces cancel out, the variable portion of a drag equation, its velocity, same here, will always be the same value in order for the object to be at terminal velocity, because it is the object's terminal velocity. Therefore, because the velocity required for an object to achieve terminal velocity is constant and unchangeable, the object's initial velocity has no bearing on its terminal velocity. Thanks for watching!